who knows what OpenStack is? Just raise your hand. So, did you try to deploy it? So, and who runs OpenStack in production or any other environment? Just raise your hand. Okay, cool, thank you. Mirantis is a company who builds OpenStack platform. So, Mirantis is one of the biggest contributor to OpenStack. Actually, it's number 2 by Stackalytics right now. So, and we develop OpenStack and we ship OpenStack to our clients. So, one of our requirements is a high availability of OpenStack. So, when we opened this question with our developers and developers of community, so they said, do we really need it? So, what do you think? Do we really need high availability in a cloud platform? So, yes, we need it. So, and we come up with some ideas, and developers said, is it so complex? So why do we really need it? Can we just do high availability on application layer? We said, okay, guys, if we do high availability on application level, then recovery time will be very high, and we will need some logic which is already written in some clustering tools to write in our application. Let me describe logical architecture of Mirantis OpenStack, and then we will go to high availability and high availability problem. So, OpenStack is actually based on several layers. One is cloud management layer. So for cloud management, we use Fuel as deployment and provisioning platform, and for cloud operator is Horizon, where they can access, create virtual instances, see utilization, run some complex scenarios, see workload on cloud, probably some other problems, but most of our clients use Fuel to deploy it and to scale it up or make some configuration. So they use two platforms on very, very high level. So on level beneath, so we have classical OpenStack services, which is Nova Compute, Cinder, Neutron, Keystone, Swift, Glance, Ceilometer, and some other services which are incubated but will be official really soon on Vancouver Summer. And on the beneath, on higher level is platform as a service, Heat as orchestrator, where you can specify deployment of your virtual instances in Amazon format or in YAML format. You may run your own application from a service catalog provided by Murana, and you may run Hadoop and data processing using Sahara. That's Mirantis OpenStack. So, and the main question in high availability, that if you need to provide high availability, you need to provide high availability for all these services. So that's amazing. So, and physical architecture on beneath is Fuel API and physical hardware for Fuel master node, and it's part of our solution is controllers. Actually, we recommend to have at least 3 controllers to avoid problems with quorum election. So, and compute services, which are connected to controllers and where actual instances are running, and storage nodes, where actually storage data is stored. So that's architecture of our solution. So it's pretty straightforward. We used tools that are familiar to most of administrators and created high availability around all these parts. So the problem of high availability. So first of all, you need to choose a solution for high availability management. So we evaluated a lot of solutions, and we come up with Corosine pacemaker cluster management. So, and our solution is based on Corosine and pacemaking. You need to organize high availability for networking. Problem is already solved, so we just used what is already solved in our solution and provided as is. So the tricky point is database. So because you need to create high availability for database, for messaging, AMQP for Rabbit, for API services, for cache and storage. So actually for database we use MySQL with Galera plugin. For messaging we use RabbitMQ, and API services is OpenStack API services. For cache layer we use Memcache, and for storage we use Ceph. Thank you, Red Hat. So why Corosine and pacemaker? Well, it's very robust and is on market for 10 years. And yes, it's very complex. So you need to understand a lot of bits and a lot of components, and the most complex thing is how to troubleshoot it. So, but that's the price for high availability. So network connectivity. We didn't try to create new tool. We just used best practices. We created mechanism to allow user to create link aggregation layer on controller or on compute nodes or on storage nodes using link aggregation with round robin, active passive, LACP, XOR. So, but as you know, so link aggregation requires configuration on switches. So that's it. So we created special Puppet module that allows you to create network topology configuration in accordance with your switch configuration to have a high availability on networking layer. So database. When we try to create a solution for high availability for database, we had some ideas, probably to use active backup, which is already known, or use Postgres, for instance. So at the time, we decided to use a Galera module, which allows to have several MySQL servers and make synchronous writes to all of them. So, but this creates another problem. As you know, CAP theorem, so is capable, available, and partitioning. So by default, MySQL is available and capable, but Galera makes it partitioning and available. So We use for initial transfer extra backup from Percona, and we created specific script for HA proxy, which creates a simple HTTP check. It's actually bash script, so it returns data in HTTP1 format with some advanced check, but that allows HA proxy to evaluate is one backend is ready or not. So backend may become unavailable for several reasons. One reason is syncing data, for instance. That's inevitable. We need to sync data when we lost connection, for instance, and we need to sync up data to the latest. So, and in this case, this node should be removed from HA proxy for a while, and when it's synced, it should be bring back online to provide high availability. So, and the problem with this, we need to know how to assemble cluster. That's the main problem. So, for instance, when you have partitioning or some problems, for instance, you lost power, you need to find the most recent data, you need to start this node, you need to join all other nodes to this node. So, and this is controlled by Corosync and Pacemaker. So we created OCF script which allows to elect primary component using data from SIB or use data saved in GraphState data. So SIB is a fast chance, so we look at the configuration information base from Pacemaker. If we find data there, and if it's correct, we use it, and if it's not correct, so we'll look at GraphState data, that file, and get data from this. So, and we run this script on all nodes, so we have like timeout penalty, like 5 minutes. If node is come up, it will register own information to SIB. So then we look for the most recent data, and we start this node as primary component. So once it's started, it's detected by Pacemaker, and on next monitoring check, it will join all nodes to the cluster. And it's pretty cool, so it works nicely. We tested it, and a lot of our customers run it on production, so which is really nice. So messaging. So we tried to use messaging and own RabbitMQ mechanism to reassemble and using mirror queues, but it didn't work. So we had some conversation with developers, and we end up with our own solution. We understood how to reassemble cluster, and we created own OCF script to assemble RabbitMQ cluster. So our first implementation was to use virtual IP that will be switched between controllers, but that solution didn't work. So it didn't work because sometimes RabbitMQ have some problems with Mnesia, and we need to delete Mnesia. So Mnesia is a RabbitMQ database where RabbitMQ stores messages for services. So if Mnesia is corrupted, it's not possible to move VIP to that node, and we need to know how to remove data. So we look a lot to Erlang code, and we created and we removed the idea of moving VIP, and we had a conversation with our developers, and they made some changes to Oslo messaging. Oslo messaging is a protocol which is used by all services for messaging, OpenStack services for messaging. And we created a patch that allows a single OpenStack service to have connection with every RabbitMQ instance, which is in mirror queue. And when we connected it, we found another problem. So that sometimes when we lose connectivity, we need to understand that we lost connectivity with one particular Rabbit node. So we created heartbeats. So we established connection with RabbitMQ instance, and we create heartbeats just to understand if it's working or not. So if it's not, so we just move to next one in the list. So and OCF script for RabbitMQ became very complex because first we need to find node who will be the first one. So for instance, it will be node number one. We start Beam, and we don't have Mnesia file. We start application, and we send notification to all other nodes to join this particular node. So when it's joined, we will start application, and that's it. So, and for status monitor, we just check it, and if we have any problems, we just delete RabbitMQ cluster and create and assemble it again. So finally, we found all problems with Rabbit, and now it works really good, allowing us to assemble it, reassemble in many conditions, like out of memory, disk problems, problems on when we have really high load, or corrupted Mnesia. So I think we covered all scenarios. So API endpoint load balancing. It's nothing special. We have HA proxy, which is proxy between end user and basic service. And all services are stateless. So we just create VIP for HA proxy, and we move it in case of problems. Meanwhile, we can restart service on that node and do some other actions. So it's pretty straightforward, very simple, just not more than 300 lines in Bash. So that's it. So Memcache. So several OpenStack services use Memcache for temporary storage. So, and firstly, we think we do need to create some kind of redundancy for Memcache, but then we realize we don't need it. We just don't need it. So if we lose tokens, user will get another token, it will be regenerated. And same for session. So if session is lost, customer will be moved out and he will be able to log in, and that's it. So we don't have any HA for Memcache, but if we move more services, probably we will require some kind of moving cache objects between Memcache nodes, which may be done by Twem proxy created by Twitter. So, but for now, our solution doesn't require proxy, doesn't require HA for Memcache and any caching layer. So storage. We use Ceph in our solution. So, and Ceph allows to create storage environment using very, just like normal hardware. It doesn't require to buy EMC or NetApp storage, which costs a lot. So we use just basic servers, some of them with SSD, some of them with HDD, and we use object and image storage sharing. So we just keep data on different nodes, and we just use internal mechanism of Ceph, and its algorithm based on Paxos, which allows Ceph internally to detect the node or actually the disk with problems. So we don't use any pacemaker wrappers to control Ceph. It works out of the box. So how we deploy it? Well, it's the most complex part, and we recommend not to deploy it manually. So if you want to have HA, please automate it. So all manual steps will create more hassle, and you will have the state which is not recoverable. So for some reason, so we had some practice. So we created a very sophisticated Puppet module for pacemaker, which allows to specify the state in declarative mode, and we had some problems with it, so we ended with some retry mechanism, as sometimes corosync locks configuration information base. So, and if I cannot write data to corosync database, so we just retry it later. So we to make changes to configuration database, we use patching. So firstly, we tried to use shadowing mechanism, but it didn't work really well. So we just get the minimal amount data that is required to insert to actual SIB, and we just insert this data, which allows us not to intersect with any other data managed by corosync and pacemaker. And we created asymmetric cluster, which is really cool. So it allows to have resources in pacemaker disabled, and when it's configured and tested, we just enable it. So that minimizes the problem, potential problem with the pacemaker. So, and one of, when we started working on high availability, we realized that we need to test it. So we look through platforms we had on market, and we didn't find any good solution for HA testing. So then we decided to write own framework for testing. So we perform destructive tests for single service, for group of service. We introduce some kind of network problems. So, for instance, network flapping or packet loss. And we do testing, performance testing during the failure. It means we just remove node, for instance, whole controller, and we perform performance testing and see if we have any degradation or not. So that allows us to see if HA is really good or not. So right now we don't have services for degradation. You can just remove one controller without any degradation or some particular service. It will work so like minute ago before the failure, so it won't be affected, it won't be noticed by customers. So we created own framework and we integrated it with CI. It means that every change we do, we test it. So and we test HA on a CI level. That allows us to see if we have some performance degradation in continuous integration, and it's integrated with our review code system. So we may use this data just to tell author of patch, just not to merge it or not to recommend it because of problems with HA testing. So that allows us to have high quality of our high availability solution and not to introduce some regression. So, and results. So, we may restart controller, so which is obvious, and actually this functionality is used by customers. So they just restart controller periodically and see if it works or not. So, and for some hardware maintenance, so they don't need to schedule any. They don't need to schedule any maintenance. They just restart it. Restart and see how it works after restart. So our HA solution allows to have network partitioning or port failure, which is good. So as hardware may fail and networking hardware fails also. So we know how to handle when we have problems with database. So we can assemble a database cluster, find the most recent data, and just use this data as the latest and assemble cluster after total failure, for instance, power outage in whole data center. So we may restart RabbitMQ and we may rebuild it in case of problems. So, and actually it's the most failing part we see on our performance testing. When we do performance testing, sometimes Rabbit is stuck and our service just restarted really quickly, rebuild the cluster, and allowing not to have any service interruption for our users. So API endpoint failure, you may restart any OpenStack API service, and it may fail actually, but it will be detected and restarted automatically. And storage node failure, it's controlled by Ceph, by its crash map and own internal mechanism. So it may find the problem with some chunks of data, replace it, sync it, so which is really cool. And since data is centralized, it may move service to another chunk, which is copy of original chunk, and use it as original, and then replicate the original chunk. So, which is really cool. So, and open issues. So every time when we have release, we ask, are we there at high availability? And right now we have problem with Neutron L3 agent. So when you have Neutron, you have networking which is tied to virtual route, which is single, and if it fails, you need to restart it. But when you restart it, you lose all TCP connection. So, and our team built some patches to OpenStack with Innovance guys just to introduce contract D and synchronize contract table between several controllers. And in case of problems, we will spin up virtual router on different controller, but we will have all connection tracking table already, and we will use it. So it means that in case of problem with Neutron, its router may be moved without losing any connection. Any data can be saved actually. So and this will be done in Fuel 6.0. We are just testing it. It will be released really soon. But it's one of problem we have right now. There are some other problems, but they're really low. So, but in general, a whole solution allows you to have as many controllers as you need to scale up controllers, to scale down controllers, to perform any kind of maintenance on controllers or unexpected. So we had some discussions with clients, and they said before HA, the reaction of problem was like 30 minutes. Right now, all problems are managed automatically without any human interaction. So their administrator and cloud operators see some events, but reaction is so fast so that problem is detected within 5-10 seconds and restarted automatically. So for cloud infrastructure, it's really important as it's the layer which all client services is relied on. So that's it. And if you have any questions or some recommendation to our solution, just feel free to ask me.